Welcome back, everybody. Today we're going to have a lesson on correlation. The big picture. To geologists, the geologic history of an area is like a story. For most, the story is written in a foreign language of rocks, some buried and some in plain sight. Only those who learn the language can decipher what the story has to tell us. One of the most important skills in telling this story is a geologic concept called correlation. Today you will learn how geologists correlate strata. It's through correlation and our previous lesson on the rules of the rocks that we can see the big picture of how Earth came to be. So today, guys, we're going to learn about correlation. And I've already at this point given you an analogy of the pages in a book and how we could put the book back together if the pages were spread all over our school. So let's just move right on to the lesson. First of all, what is correlation? Well, it's the concept in geology of comparing, matching up rock layers or strata in different locations. They could be close to each other, they could be on other sides of the planet, but the whole point is to understand the big picture about what happened in the past. So what we're trying to do is put these rock layers back together again to get a complete history, as complete as possible, of everything that's happened in the past. And you can see in this picture down below, these layers right here match up. These layers here match up on the far sides. These layers match up in the left and the middle, but not on the right. Something's happened here with this wavy line, but we know what that means from the last lesson. And these layers also match up. So that's what correlation means in a nutshell. It's just matching up layers. But there's different ways to do this, and that's what today's all about. Okay, first method of correlation we're going to talk about is a visual inspection called walking the outcrop. And you're physically going to hike or walk around where there's perhaps a road cut with rock layers visibly exposed. It's easy, inexpensive, can be fun. It is limited though, because rock strata may be covered by sediment or other rock, and road cuts are nice, but they're not everywhere. So you have to use this whenever you can. These vertical lines here, some of you might have wondered what they were. Perhaps you can write down somewhere off on the side of your notes what you think they might be, and we'll talk about it afterwards. This massive overturned fold is only visible due to this road cut. So you would never know what's going on there unless there was actually exposed rock for you to see it. So lots can be revealed by cutting through the rocks themselves. You could easily walk this outcrop, but at some point it will run out, and you can see it on the left-hand side there, it stops. But perhaps down the road a ways, you might pick it back up and try to find some of the layers in this piece to the next outcrop that you see. This guy's actually walking the outcrop. Compliments of Ward's Natural Science photographs. But these layers here, you can see continue on off the picture. Now here's a great example of correlating rock layers. This is another technique where you could use walking the outcrop in this, but imagine matching up similar rock sequences, so patterns now at different locations. This can be a reliable way to correlate rocks. And what we have here are some matching patterns of rocks in the Grand Canyon National Park in Arizona, Zion National Park in Utah, and in the far right, Bryce Canyon National Park in Utah. And by matching up the similar rock sequences, you can see how they overlap a little bit. They overlap in here, and they overlap a little bit here. But by doing that, you can get over 1 billion-year history of events taking place in this part of the southwest United States. So you have a history starting back from very old down here with the Vishnu schists and the Grand Canyon, all the way up to here, over, all the way up to here, over, and all the way up through this last formation in Bryce Canyon National Park, Utah. And that's That's close to today. It's not today. It's still back a number of million years, but you know, the Neogene, the Paleogene periods is up at the top here. They called it the Tertiary period. We used to call it that back in the day with our reference tables. But that's after the dinosaurs died out. So we have over 1 billion years of history by matching up these rock layers. A lot of stuff told here. This is the big picture. And here's our New York State map. This one looks similar to the one in our reference tables, but it's a heck of a lot prettier. And you can see all these colors, the same colors on this map are the same aged rocks. And so this has already been done by our New York State geologists. They've correlated rock types all around the state. It's a pretty neat picture, and there's a lot to it. You could spend hours poring over this picture and the back side of this poster too. And there's lots of other cool things to learn from this. And here's our version in the reference tables. And you can see it looks kind of similar, just not as detailed. Okay, third method of correlation we're going to talk about today has to do with volcanic eruptions and meteorite impacts. Both of these events leave thin layers of ash and perhaps lava in the case of volcanic eruptions. Maybe meteorite impacts too, but thin layers of this ash over large areas, sometimes the entire Earth. And these layers are deposited rapidly over these widespread areas. And the chemistry of these, what we call key beds, allows us to date the event. So if we find a particular layer and we know the chemistry of it, we know about when it happened, and we look somewhere else on Earth, we can see that, oh, that rock's the same exact age as the rock over on the other side of the planet. And it's just a very accurate way of dating certain events in history. The particular things you're seeing in the pictures here is the famous KT boundary around 65.5 million years ago. And it's loaded with a very high concentration compared to the natural concentration of a rare element called iridium. And this element's common in meteorites. So this is what we call it's kind of like the tombstone layer, where there's dinosaurs below. We see fossils of that, but we really haven't found any dinosaur fossils, absence of birds, above this layer. So this layer, the capstone layer, is the layer that separates the end of the Cretaceous period from everything after it. And this was created by an impact in the Yucatan Peninsula of a giant meteorite, which pretty much wiped out the dinosaurs. Okay, fourth method. Now this is very reliable. It's probably the best method, widely used, for correlating rock layers in different places. And it's index fossils, which we learned about in another lesson prior to this. Index fossils, remember, are deposited rapidly over a wide area. They live a short period of time. And if you find one in one area and you see the same species of index fossil in another, you know that they're pretty much in the same aged rocks. The rocks could be different types, but the same age. And you can see that actually looking, here we see this fossil right here is in some limestone, but it's the same index fossil as this over here, which is in some sandstone. So the rock types don't have to match up, but the index fossils are more reliable. And then you might wonder what happened to layer 5 here. You can see how it looks like this fossil on the right-hand outcrop has been squeezed out over here. But remember, our unconformities are missing layers of rock due to uplift and erosion. So that's why geologists hate those missing layers, because over here they never knew what existed. They could be missing out on all kinds of information, from new life forms to other things. What's the best index fossil in these 4 outcrops? Well, if you look at them, we want to find a fossil that is in all the outcrops, but only in one layer. In this case, the fossil that would best match everything up this isn't good because it's in more than one layer. Let's see. Not good. More than one layer. More than one layer. More than one layer. So the best index fossil correlates all these 4 rocks as the same age. Okay, in this last process, I'm going to save this for after the video. We'll take a look at this. We're going to go through step by step to find out the oldest all the way to the youngest rocks. It's the story, the big picture. It's kind of fun, actually. So I hope you learned something about correlation, and see you next time.